Flipping over to the last page with a couple of examples. Now, these are actually quadratic type of exponential equations. And the way that you solve quadratic type of exponential equations, and I'll explain why it's a quadratic type in a moment. Now, the first thing I would do here is, since it actually is a quadratic type, is I would subtract 12 both sides and rearrange this so there's just a 0 on the right side, and then 2 to the 2x minus 2 to the x, and then minus 12 on the left. Now, the reason this is a quadratic type equation is because that's actually 2 to the x squared, and then this is a 2 to the x, and this is a constant. So this is kind of like your quadratic term and the linear term, and then the constant. And so we're actually going to factor this. Factoring this is the same, or extremely similar, to factoring x squared minus x minus 12 and solving that quadratic equation. Okay, so again, just to show you, this 2 to the x here, 2 to the 2x, that could be written as 2 to the x squared minus, and I could write 1 times 2 to the x here, I suppose, just showing that the coefficient's 1. So this is the quadratic term, quadratic type term, even though it's got an exponential part in it. This is the linear term, and then the minus 12 is the constant on the end. So that's what I mean by it's a quadratic type. There's really a quadratic part, a linear part, and a constant part, which is the characteristics of a quadratic equation. Now, in order to factor x squared minus x minus 12, one way you can factor is to look for two numbers that add to negative 1, because there's a coefficient of negative 1 places in front of this x here, and that multiply to negative 12. And the numbers that do that are 3 and negative 4. And so that's how that factors. And of course, if you expand this out, you will get x squared minus x minus 12. Now, we're going to factor this in the same way, but instead of the two terms starting with x times x is x squared, in order for that to be a 2 to the 2x, you have to have 2 to the x and 2 to the x here, so that when I expand this out, 2 to the x times 2 to the x is 2 to the 2x. Remember, when you're multiplying things with the same base, the base stays the same, and you add the exponents. X times x is 2x. Sorry, not, well, I said x times x is 2x. That's not quite right. Remember, you add the exponents, so x and x add to 2x. You're actually multiplying these, and so you just add the exponents when you multiply them. Now, the coefficient is negative 1, just like it was here, and the numbers add to negative 12. So the same idea, it's still 3 and negative 4. So we would put a plus 3 and a minus 4, and it doesn't matter what order. Now, over here on the right side, I would set each of these factors to 0, so I'd set x plus 3 equal to 0. And I'd do the same thing over here. I'd set the 2 to the x plus 3 equal to 0. Same thing over here. I'd set the x minus 4 to 0. Same thing over here. 2 to the x minus 4 equals 0. Now, so I would subtract 3 from both sides to solve for x, so x is negative 3. So same idea here. We would have 2 to the x equals negative 3. Notice it's 2 to the x equals negative 3, not x equals negative 3. Same thing over here. I would add 4 to both sides, so x would equal 4. Same thing over here. We'd have 2 to the x equals 4. Now, notice in this exponential equation here, the 2 is a positive base raised to some exponent. Now, it doesn't matter what power of 2 I evaluate. It doesn't matter what that exponent is, positive, negative, 0, anything. You cannot have a power of a positive base ever to give you a negative. It's not possible. Like I can't multiply any number of positive 2's together and get a negative. It's just not possible. So there is no solution to that part. There is to this, and you think of 2 raised to what power is 4. You don't need logarithms for that. It's just 2 squared would be 4, so x would equal 2. Because it's 2 to the power of 2 that gives you 4. So that's the only solution, 2 to this. And we could check if we actually put this 2 in place of x here. It would look like this. We would evaluate on the left here. We would go 2 to the 2 times the 2 that we think is x minus 2 to the, and again 2, you can awful a lot of 2's here, and then of course it should equal 12, right? So we've actually got 2 to the 4th minus 2 squared. 2 to the 4th is 16 minus 4. of course, gives us 12, what's on the right side. So it does check. That is the correct solution. Okay, last example here asks to solve 4 to the 2x minus 5 times 4 to the x minus 8 equals 0. Now, again, this is a quadratic type, but actually it won't factor like this one will. There are no numbers that add to negative 5, because that's the coefficient of the 4 to the x term, and that multiply to negative 8. The numbers just don't exist. There's only a limited number of numbers that add to multiply to negative 8, like, for example, 8 and negative 1, or 1 and negative 8. Okay, and you can do the same thing with 2 and negative 4 or 4 and negative 2, and none of those pairs add to negative 5. That doesn't mean there's no solution. When you have a quadratic equation you can't factor, you go to the quadratic formula. Okay, now, so here's the quadratic formula. The difference here, of course, because it's 4 to the 2x, it's not x squared, and it's 4 to the x here, it would be 4 to the x equals negative b plus or minus and the rest of the quadratic formula. So you still fill in a and b and c the same way. A is 1 because it's 1 times 4 to the 2x. B would be negative 5 and c would be negative 8. So we fill those numbers in place of a, b, and c. And so we would simplify this. Of course, negative 5 is 5. Underneath the root, negative 5 squared is 25. And negative 4 times 1 times negative 8 is positive 32. So we're adding 32 to 25. And of course, that's 57. So we'll write that over here. Now notice one thing I changed from here to here, other than adding the 25 and 32 to get 57. Notice I just have a plus here. And the reason I dropped the negative is because if we had a minus here, if we did 5 minus the root of 57, it would be negative. Because the root of 57 is bigger than 5. In fact, it should be a little bit bigger than 7, because the root of 49 would be 7. So we went 5 minus that, we get a negative, and we'd have the same problem as here. We'd have a positive base raised to some exponent is supposed to equal negative, and it can't. Okay, so we only do the 5 plus root 57 over 2. So I want to solve for x here, and x is in the exponent. So one last time, we'll use a logarithm. And so I'll take the log of both sides, and then I'll use that power law again. I'll bring the x down and write it in front of and multiply by the log of 4. So x log 4 equals the same thing on the right side here. And so I want to solve for x, so I would divide out the log of 4. So it's this log divided by the log of 4. And that's approximately 1.325. And the calculation looks like this. Just to show that we, actually not that calculation, but the check. You can actually evaluate this in your graphing calculator or any calculator. If I plug in the 1.325 in place of x, see 4 to the 2 times that is what's here, minus 5 times 4 to the 1.325 minus 8, and it's supposed to equal 0. Now, I've rounded to 3 decimal places here, so it's not exact. But of course, you can see that it's pretty darn close to 0. It's 0.013. It's just over 1/100, so it is pretty close to 0. So that's just a way to check, of course, that your solution is correct. And that's the end of the lesson.